Me Hedgehog, where we will be getting the sponsors to come up and present with the Hire Me Hedgehog. Standing there and going, please come and work for us. Awesomely drunk.
Right.
You ready?
Well, hopefully one of these is going to serve me as a clicker. So.
Right. Massive round of applause for Ian.
Thank you very much. I haven't done anything yet, so we'll see. Right. So I was just in here for Hannah's talk about sleeping, and this was very close to my heart because I didn't really do very much of that yesterday. So if I click this, then nothing happens. So obviously, plan B. Click this. Then this is my phone's sleep report on my sleep last night, which apparently went from 2:50 till 7:30, and all the little dials are pointing to a rather grim picture. So I apologise if I'm a bit grim. So at least I can see the next slide on this clicker. So I want to talk about machine learning and data science and stuff like that. One thing that always occurs to me when I think about this is people talk about AI and they talk about all this kind of stuff. And I think that my feeling is that a lot of people don't rationally think that things are magic, but sometimes they act as though they are. And and I think this particular area, I guess probably more so for those not immediately involved in it, appears like magic. And it always brings me back to Arthur C. Clarke's third law, which states that any sufficiently advanced technology is indistinguishable from magic. And he was kind of seeing that as a sci-fi author, but I kind of see it as a technologist today, because actually we've got some very, very advanced technology that we don't really understand a lot of the time what's going on inside it. And I'm talking here to a group of people who probably have a better idea about what's going on inside technology than most. So I hear a lot about AI. And I just want to get this bit out of the way because I don't think really what we're talking about is artificial intelligence. But when we think about artificial intelligence, there's basically two flavours. And one of them is strong AI, and this is your HAL 9000 or your Terminator or whatever, a computer or a machine that is able to do general problem solving and thinking about any situation that comes its way. And the most optimistic projections of anything resembling that is, 10, 20, 30, 40 years away. So this talk isn't really about that. The other kind of AI is rather disparagingly called weak AI. And I think that is what we've got today. And it's something that can really be very helpful, but just in quite narrow domains of problems. I'm not going to talk any more about strong AI, except to say that there's this guy. I don't know, has anyone seen this TED Talk? Oh wow, you're in for a treat. Oh, except for you, you've already had the treat. This chap is a professor of philosophy at Oxford University. Now I'm a technology optimist, but this guy is perhaps less so. And he's written a book called Superintelligence, subtitled "What Happens When Our Machines Get Smarter Than We Are." And here's a picture of the book. He wrote, he's got a scenario where he sees this kind of strong AI slowly progressing by small inches as we get more computing power and other stuff like that. But at some point, it will get to the point where it's about the same intelligence as a person, and it will be able to improve itself, but it will be able to do it very fast. And so what he thinks we'll see is a massive hockey stick into machines that are much, much, much cleverer than us. I don't know what the timescale for this is, but the best thing about this book is it actually has a diagram, which I've ripped off here, called Phases in an AI Takeover Scenario. So I'm a technology optimist, as I said, but this is it for strong AI, because really the interesting thing at the moment is this weak AI, what we have today. So a couple of years ago, I thought I must learn about this because this is really, really interesting and exciting, and you start seeing really fascinating stuff happening. And I thought, well, how am I going to do this? I know I'll do an online course Because basically you can't go wrong with an online course. Well, actually you can, but I luckily didn't. So this course is on Coursera, and there's a guy called Professor Andrew Ng. I think I'm probably murdering his name. Well, not Andrew, obviously I know how to say that. He's put this deep learning specialization on Coursera, which is a set of 5 courses about deep learning, which is a particular kind of machine learning. And this is the kind of machine learning that's giving us all the miracle things at the moment. So all this stuff about natural language, understanding and recognizing images and being able to process image recognition fast enough so that you can drive a car, that kind of stuff, that's all deep learning. And I thought that's what machine learning was. I thought that's AI. I'm going to learn that. And I did. And it really, really made my brain hurt because it made me do maths that I haven't had to do for like, I don't know, 30 years or something. I'm quite old. But I had to dig out maths that was just, it just made my eyes water. And then later on, after I'd done this, I thought, well, I'd like to do more, but I'd like to understand more about what data scientists do. And so I did this course called Data Science with Python or some such, I can't actually read the name, Applied Data Science with Python. So no theory here. It's applied data science. And what I realized is I did them the wrong way around. And I'm sharing this with you so that if you decide to do this, you won't do the wrong way around. So this one had lots of useful stuff about machine learning algorithms, of which deep learning is only one. And there's all of these kind of things here. And there's these really great libraries in Python that I didn't learn anything about in that one that would have been immensely helpful for dealing with data. So these things, this stuff here, these machine learning algorithms are super simple to use. And they don't require terabytes of data, which is the other problem that we often have with machine learning. And what I'm going to tell you about is a kind of journey I did through a data science problem using some of this stuff. And just to be fair, you know, the things in this course were, after I got over the maths, which was something of a shock to my system, after I got over that, when you get into the last two or three courses in the 5, then you start suddenly doing deep learning using high-level libraries, and you're like, wow, this is amazing. And you know, I've built a cat recognizer. I mean, who doesn't need a cat recognizer? It's the fundamental building block of internet stuff. So those algorithms, it is super interesting and very, very relevant, but actually having this stuff really helped me. So I did all these courses and I thought, right, what am I going to do next? I need a problem to work on, as if there aren't enough problems just falling on my head all the time. But no, I need a data science problem to work on. And I discovered Kaggle. Has anyone heard of Kaggle? Excellent. So Kaggle is a data science kind of mecca. I probably could put that in a better way, but really what I'm trying to get at is that on Kaggle, there are data sets that you can just download and do machine learning on them. And it's got ways of evaluating it as well. So when you've made your predictions about the data set they've given you that doesn't have the answers, and you make your predictions, you upload them to Kaggle, and it tells you how well you did. And then you can iterate and do better and better and improve your score. Be up till 2 in the morning and not sleep very well. So, you know, maybe I'm not selling that very well. So the one I fixed on was the first one that everybody does when they go to Kaggle. And that is called Titanic, Machine Learning from Disaster. And the nature of this is they've got a data set that's small. In fact, the total number of rows of data that you download is 1,309. So really very, very small. And they give you a bunch of information about passengers on the Titanic. And they give you it in 2 chunks. A chunk with the answers, so survived 1 or survived 0. And another chunk without the answers. And what you have to do is build a model, predict what you think the answers are to the second chunk, upload them, and you get back a score. And so this is, I'm just going to go through quickly what I did when I was doing this. And the reason for it is that it kind of gives a bit of a flavor of what the kind of things are that data scientists have to worry about. Maybe the kinds of things that can go wrong. So that if you're dealing with data scientists from a quality point of view or from a testing point of view, you can ask them good questions. and use use a bit of their language to them, which will probably freak them out. Okay, so data science, it has two programming languages that people typically use. I mean, actually, there's probably loads, but there's two main ones. One's called R, and it looks like gibberish, and the other one is Python, and it's the best programming language ever. So, in case I've not telegraphed that enough, I'm going to talk about Python. There's been this marvellous technology that's been devised to help data scientists, and actually it helps lots of people, and it's called Jupyter Notebooks. Has anyone come across Jupyter Notebooks? Aren't they brilliant? So Jupyter Notebook is a web page, and here's a picture of one. This was my Titanic Jupyter Notebook, and what you can see here is a bunch of different fields. So here you can see I used a command in Python, tt.info, and that's the output of the command. This field, although I haven't made great use of it, is a markdown field. So what you can do is that you can take your exploration of data and make it into a story where you can write code, immediately get the results of it, and intersperse that with your notes, or things that can make other people able to understand. So there's a bunch of these things published in different places with people's whole story of how they solved a particular problem. And so this is an absolutely brilliant thing, and you can run it just on your laptop or computer, or you can run it on AWS SageMaker free for 2 months. Which is a great platform. It has all this other stuff about making your data science models into batch jobs that can run on massive data sets in the AWS cloud, which probably makes it quite worth the 2-month free trial. But I've been using the notebook server on there because it basically has a lot of, if you get the medium-sized instance with a bunch of CPUs, and if you want to do something really horrendous, you can run a notebook with a GPU-backed server that can really deal with enormous data sets. And of course, Amazon has got lots of ways of storing data, so I really like that. I also use something called Paperspace, which is very good. But you can just do this on your laptop. You don't actually need all that fanciful back end. Certainly for Titanic-sized data sets, no problem at all. That sounded really ridiculous, didn't it? Yes. For 1,500 row data sets, you can just do this on your laptop with no problem at all. So what I found myself in was a kind of iterative 3-stage process, which I've documented using a very expensive font here. So there's data preparation and management, feature selection and engineering, and then algorithm selection and tuning, and that's got evaluation in it as well. And all of these stages are iterative, and you're often going back to the one before. And one thing I realised was you have to be super organised, which you're probably all better at than me. And what I mean by that is that you're doing effectively a series of experiments on some data, and if you don't remember what the experiments were, or you don't remember, you don't keep the results, or what you have to keep this stuff organised, because if you don't, you will run into a bit of a headache scenario which I did because I just didn't know any better, so off I went, and I realised that. My best score that I'd previously got was lost to me for like 2 months. I just couldn't find out how I'd done it, which was really quite irritating. So preparation and management is a lot of that is loading the data in, looking at it. In the Titanic data, for example, there's a column called cabin. In fact, no, never mind. There's a column called cabin, and only about 30% of the cabins are filled in, because all I had was that on some stewards they found a list, and that was all they knew about the cabins. Seems funny today, where you basically, if you go on something like that, you're allocated a cabin and everybody knows everything about it from a year before or whatever. In this scenario, it seems to be much more informally run on the spot. But anyway, they found a list of some people's cabins, but not everybody. And they also So you have to look at these gaps in the data and trying to decide if you're going to do anything with them, because algorithms aren't very, they're not very tolerant of things like data gaps. I'm just finding out how far through I am. Sorry, I just realised I was looking at a number that wasn't going up. And that's the wrong thing. I'm halfway through. Okay. So features are the data things that you're going to put into the algorithm. And it's not always the same as it's hardly ever exactly the same as the data that you're given to start with. So for example, in the Titanic data, you're given age for the various passengers, and you're given their names and titles. And from that, you can infer a column called child, where you can say, if you're a child, this column will have a 1, and if you weren't, you have a 0. And you do that when you can come up with, basically, you know something about the real world, you know something about the data. You can come up with a thought, I know that on the Titanic it was the lifeboats, it was women and children first. So knowing the gender of people, knowing their age, you know that was happened, but the algorithm doesn't. So you need to find ways to tell it. And then down here, the algorithm selection and tuning, that's all about picking one of these algorithms that I mentioned earlier, or another one. And actually, the big news of this here is that this one here, this step here, has far, far more impact on the outcome and the accuracy than this step here, picking the algorithm. So people love picking algorithms, and you can write wonderful scripts that try 300 algorithms and tell you which one had the best score and all this kind of thing. But you're tuning the edges. The most vital and important thing to get more accurate predictions is to do the right feature engineering, and that's where most of the work ought to be. So here is a bit of the Titanic data just to show you. So this survived column is this is what contains the thing you have to guess. So some of these things have got NaN written in them, which stands for not a number. And this is because I concatenate it to do this. I concatenated together both the training data set and the data set that I have to do the work evaluating. So the NaNs those are entries from the data set where you have to make the predictions. Not a number, yes, I've said all that. But you can see some of these other columns. So I talked about cabin, name, sex, age. This SIBSP, did I say that right? Any advance on SIBSP? And Parch, these are about how many siblings were they travelling with and parent-child relationships. And actually, once you dig into it, you can start seeing this information in other places as well. The ticket is a big gibberishy text field with lots of inconsistencies. The fare, again, and the embarked is where did they get on. And so they got on most of them got on at Southampton, some people got on at Cherbourg, and some people got on at Queenstown in Ireland. So what you have to do is you load this data in, and the first thing you have to do is try and dig into it and understand it. And this is why Python is the best. You can do this same thing in R, but who knows how to do that. So what I've done here, you can see the code that's produced this is relatively very simple. And actually most of the whole third of it down here is just setting the titles on the boxes. So this Python library matplotlib and Seaborn, the main sort of things I've used here, let you visualize the data. And so you can start looking at it and you can say, wow, it was a bad idea to be in third class if you want to survive. And some of the inequalities in this that you can immediately just look at in this data are stunning. Look at this. Which one is this? Parents, child. So traveling alone was bad, and there's quite a few other interesting things here, but I'll probably run out of time if I talk about them to the level which I would like to. But then, you know, who's got that much time? So there's another useful visualization. This here is basically showing the data level, the data occupancy of this is basically showing the nulls in the columns. So survived here, you've got a big block of nulls. That's the data set for predicting. But you can see there's quite a few ages missing and lots and lots of cabins missing. And there's one or two in some of the others. And so in my my Jupyter notebook, which I'm actually happy to share if anyone wants to see it, it's a bit embarrassing at the moment because it's so messy and you can just learn how not to be organised. But you can see that just the code for doing that is 3 lines at the top there. This is a listing of the columns and it's showing which ones are nulls. So you've got 1309 entries, but only 295 cabins. So again, digging into the data, understanding what you've got and what you might need to do. And there's a bit of patching up that I did, and then undid some of, I have to say. But this was some stuff that I had done in March to try and prepare this data. So one thing was I added a title column. And I got that by mining it out of the name, because the names were all Mr., Mrs., Master, and then there were some sort of outliers like the Countess, but there were some aristocratic titles in there. There were some, needless to say, if you had an aristocratic title, that was a fairly decent predictor that you would survive. Age, I put some median ages in, which I used the titles for actually, because that seemed to be a better predictor than just using a median. There was one missing fare, so I just put in it was in 3rd class, so I just put an average 3rd class. So you can do stuff like going through these things and making them better, patching some of the holes. But you can't patch the holes that are in cabin, because there's just no sensible way to do that. But some of these other things you can. And data is tricksy. And it's unexpected. It behaves in weird and wonderful ways. One thing I've did here was I split the passenger class into 3 separate columns, which were basically bools. So, pardon me. So if you're in 3rd class, you've got a 1 in that one and a 0 in the other 2. And the reason for doing that is that somebody in 3rd class is not 3 times anything of somebody in 1st class. They're not numbers really, they're categories. Although they are ordered categories, so you do lose something by doing that. Other things there, I did the same thing for the titles, but I love I found this on a website, and then I thought, well, rather than give you the website, I'll just write it in terrible writing. But you have these different kinds of scales. So, what's double 2 meters? Anybody? Come on, double 2. Well done.
Thanks.
I wish I had a prize, but I don't. Sorry. I should have bought something. So yeah, that's absolutely the case. But what's double 2 degrees Celsius? You can't do that, and that's because it's a interval scale. And then you've got ordinal scales like grades, where A is better than C, but you can't really say how much by. Nominal scales, which is basically categories, unordered, and then ratio scales like length, which is simply a very normal number. So all of these things, algorithms don't understand the difference between these numbers. So you have to try and find ways of communicating to the algorithm what that is. So that's what that trick there of splitting them into flags, effectively, it was one way of doing that. This is me, and now you think that was, I'm going to have to speed up now. So 892 records in the in the training set that they gave me, and in order to work with this, what you have to do is you split off some of that data where you've got the answers, and you sequester it somewhere, and you use it to evaluate your model on the rest of the data you've got the answers. So rather than every time you do something uploading it to Kaggle, you actually got a baseline that you can use to evaluate it on your computer. And then the challenge set, which are the ones you have to finally do. And they wrote this utility function, which is actually gone again, but to split the data like that. And one thing I did run into was my model seemed to be doing really, really well, except when I put it on Kaggle. And the reason was that I'd done some things that meant that my test set data was being used for some of this processing. And therefore, actually, my model was better at evaluating that test set than it should have been. So that's why you have to keep that test set sacredly apart, so that your model never sees it and it provides a realistic representation of how well it's going to do. So this data leakage is a massive deal, and if data scientists are having problems, that's always a good place to put the magnifying glass to start looking at what exactly they're doing. As I said, algorithms, not so important, but I've got a useful list of them here. I guess I can find a way to share these slides if people want them. So when you finish reading that, just let me know. Yeah, that was a joke. I've had fun with random forest algorithms. That's very good for Titanic. Gradient boosted trees, there's something called XGBoost, which is a sort of super algorithm that's not deep learning, but it's really, really good for some data sets, and it's like almost like magic, it seems sometimes. And then deep learning, which is what I talked about that before. But this is a decent list of some deep learning, some machine learning algorithms that you can use. So one problem that data scientists deal with a lot is something called bias and variance. So bias is basically how right is your model effectively, and if you've got too much bias, that means that your model is not learning enough from your training set. And then there's something called variance, which is means that it becomes very, very, very good at your training set, but when you try and use it on data it hasn't seen before, it doesn't work. And this is like the devil. For data scientists are always trading off these two things. I've got an illustration which I'm going to run through very quickly. So imagine you've got just two features and you can plot them on a graph like that. And what you're looking for is an algorithm that can separate them as best as possible, so that if you then put another one in, it would be able to predict it. And so this model is very simple because it's just a straight line. But so you can see it's a bit underfitting, because actually it doesn't really cater for those red ones that are on the wrong side of the line. And there are some blue ones on the wrong side of the line as well. So let's say that you thought, well, I need to fix this. I need a much more complicated model. And you had one that was like that. That's fantastic. That works perfectly on your training set. But what if you then give it some data that it hasn't seen before? Then you're into, oh dear, that's not really very good. So that's overfitting. That's basically where your model, your algorithm is too sensitized to the training set, so that it can't really comprehend data it hasn't seen before. So that's what I just said. Yeah, thank you. So this might be about right. Actually, an algorithm that came with a curve like that. If I add those points back in, you can see, yeah, there or thereabouts. There are some outliers. There's that blue cross up there. But really, do you want your model to be going through contortions just because of that one outlier? No, you don't. So you need it to be ignoring those things. So this, yeah, if it's about right. And here's a guy on Kaggle who published for different algorithms. He's got the red training score and the green cross-validation score. So the training score is the score on the training set, and the green line is the score on effectively a test set. So you can see some of these algorithms, they're basically exhibiting bias and variance and all that kind of stuff, which again I feel is a rabbit hole of monumental proportions, so I'm going to skirt around the edge delicately. Another interesting thing is some of the algorithms can provide you with feature importance, which is really, really interesting. So once you've trained it, it tells you which one of the features most influenced its decisions. I'll zoom in on that one a bit. So for this one, which is this guy had used a number of them, you can see the gender of the passenger was incredibly important to it, and the fare, and whether it was in third class and age. And then when you get down here, you're basically saying, well, this is all just irrelevant, almost invisibly contributing to the algorithm. So whether you were on deck A is almost irrelevant. And there was some. So this is a 2 o'clock in the morning thing from last night. This is the feature importances from my current XGBoost based effort. And you see the second line there is family survival, which is a story of torment that kept me up all night, and I'll tell you it if you come and see me later. Cross-validation, there's a ton of stuff in here. It's very interesting. This is the code to run the model. And it's got various things to find this grid search to find the best parameters for the model, all this kind of stuff. As I said, much less important than getting the data right. Benchmarking predictions. So this is embarrassing. So my ego wanted me not to publish this, but I have. When you're looking at the data, one thing you can do is do some really simplistic predictions and see the scores that you get. So I did 3. What if I just predict that third-class passengers all perished and the rest lived? And immediately I got a score of 0.64. So you're thinking, wow, so that predicted quite a lot over random. Then if you say women and girls live and men and boys perish, it goes up to 73. And if you say women and children live and men perish, it goes up to 77. So what I'm really saying by that is, if my machine learning model is scoring 76, then I've done a lot of complexity for almost no reason, because that simplistic version actually does a better job. I made this list of what can go wrong. I'm sure it's about, I could have made a list in a much smaller font. Feature identification, data leakage, and one important one that I haven't mentioned is this evaluation metric. When you're evaluating your model, you want to score it in a very particular, in a way that's actually helpful for real life. And if you pick the wrong scoring metric, then you're tuning your model to score highly in something that actually it's probably not working for real life. You've got to make sure the model complexity is right. So in March, ta-da, I was 2,106th, yay, on the Kaggle Leaderboard. But, whoa! I'm about to have an altercation with a fire extinguisher in my excitement. Drum roll, please. June, 2 o'clock in the morning, 1,700, yay! And I think that was about 0.2% difference in the score. So all I can say now is few, or if anyone's got any questions, and if you want to talk about it more, come and talk to me, because I love arm waving. So as you're probably told by now. Gentleman over there.
Do you have an algorithm to predict what rank you're going to be in the future?
Well, obviously I do, and it's showing a very straight line going up into the happy world of happiness.
Can you use the output as training data again, or was that just increased bias?
Well, what you'll be doing then is telling the model stuff it already knows. Yeah. So the best case is it won't make any difference, but it might probably, likely for some complicated reason, it will make it worse. So yeah, if the model's made predictions, basically what you want to feed the model with is only real, stuff that matches the real world.
Anything else? Yeah?
Is there a perfect algorithm to show exactly who survived and who died?
Well, you can look it up on Google. And so if you go to Kaggle's scoreboard, a lot of the top people on the scoreboard have got a 1.0 score, which they did not get via machine learning, but by visiting Wikipedia. So I think the most you can actually get with algorithms is there are people with 84, 85. Frighteningly. And Kaggle has a load of other stuff. It's not just this, but this was just a journey through that particular experience because I thought it's interesting. I hope it was interesting. All right. Thank you.